Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Ira Rothstein, who is a professor of physics at Carnegie Mellon University. He is interested in diverse topics in elementary particle physics, gravity wave physics, astrophysics, cosmology, and QCD. In the realm of high-energy physics, he uses the data from the LHC to explain the origin of mass and the nature of the dark matter. Welcome, Ira.
Hi. Thanks for having me.
Thanks for doing this. So I want to start with one of your recent papers entitled An Effective Field Theory of Quantum Mechanical Black Hole Horizons, in which you say we develop an effective theory which describes black holes with quantum mechanical horizons that is valid at scales long compared to the Schwarzschild radius, but short compared to the lifetime of the black hole. Before we get into the details of this, Ira, a black hole is sort of a discontinuity in space-time when you have a large amount of mass concentrated in a short space-time. And it basically becomes something that we don't quite understand. It's undefined, right? And because of its characteristics, we call it black hole because not even light can escape from it, right? So could you define black hole along those lines?
So you did a pretty good job yourself. Basically, it's if you have a region of something very, very dense. So if you took the sun and compressed it to a few kilometers in radius, its gravity would become so strong that it would just collapse, and it would form what's known as a horizon. That is, you can imagine it's like a ball that's encompassing some region of space from which nothing can escape.
Right.
So it's called a black hole because not even light can escape. And if anyone or anything were to fall in, no matter how hard they tried, no matter how powerful of a rocket they had, they could never actually escape the hole.
Right.
Escape the horizon, which is the sort of the radius from which you can never escape.
Yeah. So if you take the sun and crunch it down to the size of Manhattan, it will become a black hole.
Yeah.
And we don't know what is in there because ultimately, it's not like a neutron star. It's not something that you can touch and feel. Essentially, it's a discontinuity in space-time. And so the reason we say that light cannot escape from it is that the gravitational effects of a black hole is so high that light behaving like a particle will be pulled in, right?
Yep.
Okay, so
exactly.
So I know that the idea of a black hole came out of general theory of relativity from Einstein.
Yeah. Schwarzschild discovered it a few years after Einstein. He discovered the mathematical theory of black holes shortly after Einstein's theory was developed.
Okay, and I know that the recent Nobel Prize, I can't remember the names, but it is sort of, it's not black hole per se, but a very dense object at the center of our galaxy, right? Which is
Yeah,
considered to be a
yeah,
black hole.
yeah. Oh, yeah. It's a huge black hole. So we believe that almost every galaxy have black holes this with masses, tens of thousands of the times of the
Yeah.
sun. There are also smaller black holes which have masses around a few times the mass of the sun. So there are different types of black holes, but usually at the center of galaxies, there's a huge black hole which has been accruing matter over the lifetime of the universe, and that's how it got so big.
Yeah, so for the Milky Way, then we think we have a supermassive black hole, right? It's is it billions of mass of sun?
Yeah, I'm not exactly sure of the exact
Yeah.
number, but it's a lot.
Okay. And so there were some measurements taken over a long period of time of stars going around that center. Again, we cannot see a black hole, but we could impute the existence of something there because of just the
Right.
movement, right, of the stars around it.
Right. So how do you prove the existence of something you can't see?
Yeah.
That's a problem. So, in the case of the black hole at the center of the galaxy, or in general in any black hole, we all have always inferred the existence of the hole from stuff falling, light falling in and then becoming black, right?
Yeah.
So you see stuff coming in and you see nothing coming out. You see darkness. But in 2016, we actually had direct confirmation of the existence of black holes from the Gravitational Wave Observatory. So probably your listeners may have heard about this discovery, which also won the Nobel Prize a few years back. There are something called the Large Interferometer Gravitational Observatory.
Yeah.
There are two of them in the U.S., and they detected the collision of two black holes. And you could ask, well, if they're black and they're colliding, meaning they don't have any light, how can you see them? And the answer is that when they collide, they generate what's known as a gravitational wave. And a gravitational wave is actually like a ripple in space and time, like a ripple in a pond.
Yeah.
And it traveled to us and passed through the detector. And the detector was able to recognize the signature of the waves that came from a black hole. So different types of black holes of different sizes collide, and depending on how far away they are and how massive they were, they send different signatures. And from these ripples in space-time, which are measured at these observatories, you can infer the existence of a black hole, in which case, and those signatures are fingerprints, and we know what the fingerprint of a black hole is, and that's part of what I do in my work, is try to find what would the fingerprint look like. And amazingly fits exactly the fingerprint of a black hole. So we have overwhelming evidence now for the existence of these objects in our universe.
Yeah, and folks still want to see it. I think the Hubble pictures got everybody's imagination running. And so we have something called the Event Horizon Telescope that's getting some data that we cannot see the black hole, but we could actually see a picture of some sort, right?
Right. Yeah. So I think they have some computer enhanced pictures of, you could see what's around the horizon. So it's rather remarkable what they can reconstruct from the horizon of the hole.
Yeah. So that is it's not done yet. I guess that's in process. And so going back to your paper, effective field theory of quantum mechanical black hole horizon. So what exactly is effective field theory?
This is my favorite subject. So it's a term that probably most laymen have never heard of, and yet it's so crucial to science. So let me just start with a historical anecdote.
Yeah.
So, how did science progress? Well, if we talk about, I'm not a historian of science, but I can randomly pick an event. We can talk about Newton first understanding. Of course, science goes back much longer than that, but let's pretend. Newton was able to figure out the laws of motion, F equals ma, how something slides down a block.
Right.
Now, Newton didn't know anything about atoms. He didn't know how atoms interacted. He didn't know, he didn't know how the atoms of the block would interact with the ball. With the slide, with the brick it was sliding down.
Yeah.
So how is it that Newton didn't need to know atomic physics in order to be able to figure out how a block slides down a plane? Did that have to be true? So you can imagine a universe where the laws of a block sliding down a plane necessitated an understanding of atomic physics. If that were true, he would have never figured out F is equal to ma because he didn't know anything about atoms.
Right.
So that is a question that, I ask myself, and maybe some listeners have asked themselves. And the question is, why is it possible to learn about big things without having first to know about small things? And that is the essence of effective field theories, even though it sounds very technical, but it's really the question of why is it that we can learn about big things without knowing about small things?
So at the scale of the universe, if I understand this correctly, Ira, at the scale of the universe, the theories we could postulate do not maybe require a very detailed understanding of the interactions. Is that yeah.
Right. Well, yeah, exactly. So for instance, if we're looking at, cosmological questions, does it really matter if I understand how a star burns? Right? Not really.
Yeah.
Right. So it's the same idea, is that the science at long distances becomes it becomes less sensitive to the science at short distances. So I didn't need to know about the Higgs boson in order to figure out elementary problems that we study in high school, right? About any of those basic mechanical problems. And the question is, did that have to be true? And there are some deep underlying physics reasons why it actually is true, that the nature of long distance science doesn't care about short distance science. If it did, we couldn't have understood biology until we couldn't understand how the heart worked until we understood how cells work.
Right.
It's the same principle, and that would have been terrible. We would have never progressed as a society had that been true.
Yeah. So, but in the area of cosmology, though, Ira, I mean, I don't know much about this, but I'm just throwing this out to get your insight. In the area of cosmology, if you rewind time back, we get to the Big Bang, we get to the inflation area. So we are actually talking about really small stuff there, right? So is cosmology sort of different in that context?
No. I mean, certainly we need to understand, fundamentally, we need to understand what happens at short distances in order to explain what's happening at long distances. So if you really want to understand why the universe is the way it is now, it's not that it doesn't care at all about what happened at short distances or at early times when the universe was first born, right?
Yeah.
The distribution of stars and matter throughout our universe is very sensitive to that. But I don't need to know the theory of what happened immediately after the Big Bang in order to figure out how stars are moving now. Now, I may need to know everything that happened in early times to know where the stars are, right? But once if I don't ask that question, I can still figure out the dynamics of stars without having how they originated, right?
Yeah, so it depends on your objective, I guess. So
that's right.
Right. So like you say, if Newton went about his work and he assumed that he has to take that ball and cut it into pieces and into smaller and smaller pieces before he can understand F equal to ma, he would never have gotten there.
Yeah.
So in some sense, what you're saying is that if your objective is to understand things in a large scale, maybe maybe your ideas, and I'm going to make a statement, you can correct me, maybe your ideas get a bit clouded if you really get into the details of it. Is that?
So right, so what you can confuse yourself
Yeah.
by forcing yourself to try to understand what happens at really short distances
Mm.
instead of sort of trying to say, okay, well, I don't know what happens at short distances. I don't know what the mass of the electron is. Let's think about that, right?
Yeah.
In terms of the ball. But maybe the mass of the electron doesn't matter. All that matters is the total mass of all the electrons in the ball,
Right.
right? And if I thought that I needed to know the mass of the electron to understand how the ball rolls, well, then I'm never going to figure it out, right?
Yeah. And
And
Einstein is a good example of this, right? I mean, his theories are also, not, it's conceptually so elegant and it describing what is happening without quantum mechanics, right? Without getting into the details.
well, he certainly, when it came to his discovery of relativity, yeah, there was no need for him to go into microscopic physics in order to figure out the laws of relativity.
Right.
Yeah, that's absolutely true. Yeah.
And so talk about black holes in this context. So what is Schwarzschild radius again?
So the Schwarzschild radius is the radius um, uh, at which nothing can escape. So if you think about a ball, then the Schwarzschild radius would be like the radius of the ball, and anything inside the ball would be inside the Schwarzschild radius. That would be inside the black hole where nothing can escape.
So
And
so that'd be the event horizon then for the black hole?
that's the same thing. The
Okay.
event for Schwarzschild black hole, the event horizon and the Schwarzschild radius are the same thing. Yeah.
Okay. And so when you apply effective theory to black holes, so what's the gist of what we
Uh-huh.
can say there?
Right. So the question is, if I want to understand the behavior of black holes at long distances, I want to say I don't need to know the microscopic behavior of the black hole, which we don't still quite understand,
Mm.
right? So basically what my collaborator and I, Walter Goldberger, at Yale did was to figure out a way to effectively describe the black hole as a point particle,
Mm.
but a point particle with very special properties. And we imbue the point particle with the properties so that the point particle is effectively acting like a black hole.
Mm. Okay.
And at the same time, we don't have to understand all the details because exactly for the reasons that you and I had just discussed.
Yeah. So if you create something, a point particle, as you say, with all the characteristics of black hole, then you can basically forget what is happening inside the event horizon. You can
Correct.
have lot
Yes,
of predictions, right? Yeah.
exactly. Which allowed us to make new predictions that hadn't been made before.
Right. Okay. And so how does the quantum mechanical aspects come into that? You say in the paper, our formalism allows one to calculate the quantum mechanical effects and scattering processes involving black hole asymptomatic states.
Exactly. So, if you try to, we still don't understand the details of how the quantum mechanics of black holes. So, just as a little bit of background, so black holes were discovered, theoretically at least, were proposed by Schwarzschild in the early 20th century. But in the 1970s, so as we were talking about before, black holes were thought to be completely black. Nothing ever came out of them. They were dark.
Yeah.
Until Hawking found that mathematically it was inescapable that black holes actually evaporate through quantum mechanical processes.
Mm.
So that while they look black, they're actually constantly bubbling, they're evaporating.
Right.
And little particles are coming in and out of existence near the horizon, and some of them manage to escape outside the horizon. And it looks exactly like a hot object with some finite temperature. So anything which has a temperature emits radiation, and black holes have a temperature, remarkably, and they emit radiation, and eventually, if nothing else fell in, they would eventually disappear.
And so if you get black hole particles, so to speak, So can you get to Hawking radiation in that
Right. So
framework?
you would think, well, whatever's causing the black hole has to do with on inside. So how could we ever get a particle to which has no size to actually evaporate? And so what Walter and I showed was we're able to imbue the particle with certain properties that allowed it to actually evaporate mathematically. And in so doing, because we're now treating it as a simple particle, there are things we could calculate that we couldn't calculate before if we were trying to solve the big problem, right? So it's sort of a divide and conquer where you simplify the problem, which is what in science we try to find the simplest model to give us the greatest power to understand and use it to predict things. So by treating it as a point particle and yet imbuing it with these characteristics mathematically of Hawking radiation, we were able to calculate things that weren't calculated before.
Okay. Um, just for my own understanding, Ira, so I was told that the Hawking radiation, one mechanistic, sort of explanation for it is that at the event horizon, you have a particle and an antiparticle. An antiparticle goes in and the particle escapes, and that is how the radiation happens. Is that still the
Yeah, no.
understanding, or yeah?
And
Okay.
so the trick was, well, if you have a particle, it doesn't have an event horizon. It doesn't have, so what does that mean? And that's where the effective field theory techniques that we developed came into play, where we were able to essentially mock up all the stuff going on at the horizon and sort of stick it onto the particle in a mathematically consistent way.
Mm, mm. And this radiation and evaporation still happens in that
Yes, absolutely. It
framework.
reproduces everything, every prediction at long distances that any normal black hole would have.
Okay, okay. We'll take a quick break, Ira. When we come back, we'll talk more about Hawking radiation. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com. So we are back, Ira. So we are talking about black holes, Hawking radiation, properties of black holes, and the effective field theory, which simplistically put might be described as when you try to define interactions or actions, I should say, in long distances, perhaps we can reduce the details into a framework. So in the case of a black hole, you in effective field theory, if I understand this correctly, Ira, you reduce the black hole to a particle. And that allows you to actually focus on sort of what the black hole would do to the universe type questions, right?
Yeah, that's exactly right.
So one of the important properties of black holes is the Hawking radiation, and this is something that Hawking discovered, and essentially the discovery of this has some implications for the life of the black hole, right? Ultimately, we expect a black hole to radiate away completely.
So in isolation, it would radiate away completely. And that actually led to one of the most pressing problems in theoretical physics today, which is the amazing thing about black holes when they radiate, the way they radiate is independent of what fell in. So if you threw a car into a black hole, or if you threw an encyclopedia into a black hole, when the black hole evaporates, it doesn't care. The fingerprint of the black hole seems to be independent of what you threw in. And so why is that a problem? Well, because one of the fundamental laws of science or in physics is conserved. So
Yeah.
you can't get rid of information. So, which supposed as soon as Hawking made this discovery, because if I threw a encyclopedia, many of your younger listeners probably don't know what an encyclopedia is.
Right.
But if I threw a computer with a memory and 10 gigs of terabytes of memory into a
Yeah.
black hole, that's a huge amount of information relative to, say, if I threw in a sock, right?
Right.
So,
Right.
but when the black hole evaporates, the final state doesn't care if it's a sock or if it's a hard drive. So the
Right.
question is, what happened to that information? And that's the information paradox, and is one of the most pressing problems in theoretical physics.
Yeah, I mean, that's an amazing thing, from, again, without knowing the details of it. The black hole has ultimately only three properties, right? Its mass, its spin, and its charge. And charge you can probably ignore in most cases. So it actually technically has only two properties.
Yeah,
And so that actually, going back to effective field theory, so that actually allows you to reduce that into a particle with just two properties.
exactly. You hit it right on the head. That's right. So black holes are perfect, right? And they're all exactly the same.
Yeah.
If two black holes with the same mass and the same spin are completely indistinguishable, and that's just like an elementary particle, right? Just like all electrons are exactly the same. So black holes, in some sense, are truly fundamental particles in that way. And because they're so simple and they only have mass and spin, we can just treat it like a particle with mass and spin.
Yeah, it's an amazing thing. It's, there are billions of sun's mass in there in a black hole, but you can actually consider that to be more like a quark
Yeah, and
with,
it's
yeah.
elementary. It's a perfect object, right?
Yeah, yeah. So you talked about gravity waves, and so LIGO, which was an experiment that has been going on, and one of the excitements. When was the first gravity wave detected? A few years
Yeah,
ago,
2016, at the end of 2016, I believe.
2016,
Yeah,
and this is a huge engineering marvel.
unbelievable.
Uh,
Yeah.
yeah, it's about a mile long tunnel, is it?
Yeah, it's two arms that are a few
Yeah,
kilometers long, and it took over 30 years to build it. And the most remarkable thing, well, aside from its scientific achievements, is that no one really knew if it was going to work.
yeah,
And people poured their lives into it. Some people worked on it many years and never, didn't live to see its success, because a lot of people really didn't think A, it would ever work, or B, whether or not it would see anything. It would be like a telescope that had no eyes, right?
yeah, yeah.
And it's a tribute to the National Science Foundation, which funded it, which is a government agency, um, that they persisted, and it was an amazing human accomplishment, really unbelievable.
Yeah, and again, from an engineering perspective, I think the measurement taken there with mirrors is like the radius of an atom or something
It's the
like that,
most
right?
precise measurement made. Yeah. So
Yeah,
the arms. So what happens is there's a laser that's being fired between mirrors, which are a mile apart.
yeah,
And when the gravitational wave comes through, it moves the mirrors less than the radius of a nucleus of an atom,
right.
and yet it's able to be detected. Right. So it's one part that you're measuring one part in 10 to the 24. Right. That's unbelievable. It is
Yeah.
really mind-boggling that this has been accomplished.
Yeah, so in your framework, in effective field theory, when you reduce it to a particle, you could actually predict the existence of or even the properties of gravity waves when two black holes merge,
Right,
right?
right. So we use the effective field theory. It's a lot easier to understand. So I should first say we should first say, so how do the gravity waves show up? So what happens is two black holes, if they're
Yeah,
near enough to each other, they orbit each other, And as they do so, they emit gravity waves and lose energy, and they start to in-spiral. And as they in-spiral, they emit more and more gravity waves, and those signals are what we measured Earth. And to actually solve for the motion of two real black holes has to be done on a computer. But what Walter and I did was we said, well, if we treat them as point particles using effective field theory, then we could solve the problem in a much easier fashion. So as long
Yeah.
as they're far enough apart from each other that they don't merge, then they're treated as individual particles, then we could make predictions for the gravity waves without having to resort to writing computer code.
Yeah, so as they dance with each other, I would imagine there are different gravity waves being generated, right? It's not only at the point of merger, is it?
Right, yeah, correct.
Yeah.
Yeah, absolutely.
And so, did LIGO have sort of a history of gravity waves coming from this one event?
No, so you mean the first event that they saw?
Yeah.
So they were taking they take data continuously, and you remember this machine is so sensitive that when they were in Louisiana, if there was a large wave crashing on the coast, right, or
Yeah.
or if there was a truck driving anywhere near this underground detector, so it's an incredibly sensitive machine,
Yeah.
and they saw the signal, and so how did they know it was black holes colliding? And the answer is that they have basically, if you think about from the point of view of a police department, they have catalogs of fingerprints, right? That's called
Right.
they have what's known as templates, and then the computer compares the signal to all these possible collisions until they find one that fits the signal. And if you go online, I recommend your listeners can go to the LIGO website, and you can
Yeah.
see the signal versus the prediction for certain masses of black holes, and they like sit on top of each other. It's unbelievable. I highly recommend people go to the LIGO website and check it out.
Mm. Is this the black hole merger? I would imagine is a fairly common event,
Yes,
right?
absolutely. It's happening. So since 2016, and they've
Yeah.
increased the sensitivity of the detector, there's now hundreds of events. And as the sensitivity grows, events are coming in at a rate that they barely have time to keep up with. Because
Is
these are extactic events, right? These are things coming
Yeah.
from nearby galaxies, and as you know, there are many galaxies, and so the probability of these things happening is pretty large.
So do we have an estimate of what the, sort of the frequency? Uh, I mean, this is looking out to the
Right,
universe. So anywhere two black holes merging, it will create something.
absolutely. So, but they have to be large enough so that we can see their signals, and not so far away that
Yeah.
the signal becomes too weak. So I think the expected event rate is pretty close. Actually, it's a little bit larger than they originally thought. So it's on the order of tens or 20 a month.
Wow.
Yeah.
Okay. And that's something that you can prove actually with your model.
So the event rate is something we can't prove. The event rate has to do with star formation and densities of stars and
Oh,
regions. So what we
yeah.
do is we assume that two guys are going to collide. And if you give us the mass, and for a given mass and spin, then we can
Yeah.
basically tell you what the signal is going to look like.
Okay. So you have a heuristic that they can measure
Yes. So
if
so I
yeah.
mean, I should say what really happens is we give the experimentalists formulas for the characteristics, and then they take it and they do very complicated analyses on it to make it, to take that sort of raw prediction and make it to one which incorporates all the errors of the detectors, and all the details of the experiment. They
Hmm.
do the hard work, is what I'm trying to say.
Yeah, yeah. So, so in conclusion, Ira, so does this have any implications for everybody's trying to get gravity into a theory, right?
Yeah, yeah,
Into a grand
yeah.
unification. Does this have any implications for
Well,
that?
I think in a tangential way, in the sense that we're able to calculate, we're able to understand better the quantum mechanics of black hole horizons. So in that
Yeah.
respect, one of the key aspects of understanding gravity and quantum mechanics at the same time, a place where they are sort of naturally married is at black holes. So many researchers have focused their attention on, or people interested in quantum gravity and understanding the quantum nature of black holes in the hope that it sheds light on how we incorporate quantum mechanics and gravity.
Yeah, so since you reduced a black hole into a fundamental particle, will a graviton look similar
Yeah, so
if it existed?
absolutely. So as
Yeah.
long as you're looking at gravitons whose wavelength is large compared to the size of the object, it will look like a particle and it will produce the right result.
Right. I know that there was some hypothesis around, a large number of small primordial black holes
Uh-huh.
created at the beginning of the universe, right? Um, and there is still, a search for the dark matter and so on. Uh, are there any implications there with this idea?
I don't think so. Primordial black holes are interesting possible dark matter candidates, although there's serious problems with it, and I believe it's become rather disfavored as a.
Mm.
But
Yeah.
no, you certainly could use our formalism to describe those objects, but it's not clear to me, given especially that we don't have any evidence for their existence or how we would look for them, that it would be useful in that direction.
Yeah, I mean, it's fascinating. You have taken one of the largest sort of heavy object in the universe and made it a fundamental particle.
Yeah.
And so it's coming full circle.
Well, for the
This-
same reason Newton was able to understand the block sliding down the plane, we were able to understand black holes in this way.
yeah. Excellent. Yeah, this has been great, Ira. Thanks so much for spending
My
time with
pleasure.
me.
My pleasure.
Thank you. Bye. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.